Right, everybody. Today we are going to move up to some of my favorite stuff in computer networks, which has to do with the transport layer. As always, we are leaning on this book, Computer Network Systems Approach, pretty heavily as we move into this. So we've talked about the network layer and the IP protocol and how we can ship information from computer to computer. Right, you drop the IP address along with your data, and then these routers kind of figure out where to drop things off and their direct links to get things to where it wants to go. Right, that's great. But once we move to the transport layer and hopefully eventually to the application layer, we need to know how to get this information from place to place. Now, there are a couple of transport layer protocols that are very popular. One's called UDP, and UDP is basically the dumbest transport layer that you can stick on top of IP. It's a demultiplexer only, and its job is basically just to ship these things to the appropriate place. So I like this mailman analogy that we were using before. When you write an address on an envelope and you give it to the mail people, they deliver it to the address, and then that's that. But once you have those, a bunch of letters, let's say, at an address, they'll have names on them. And so the UDP layer, and this is the unified datagram packet, so we're talking about packets for sure. Its job will be to figure out like who actually gets this envelope and which application gets this envelope. And the way that it does that is via a port number. Port numbers are 16 bits. They go from 0 to 65535. That gives you about 64,000 of them, right? Or 65,535 almost. And so what your system will do is it will have some connection based on your IP and port number, and it will make a socket, and UDP will show up and deliver to your OS, hey, like here's a packet, and it will push it in that socket based on the port and IP where it's supposed to go. So UDP is pretty simple. When you look at the header that you have to create UDP, it is literally as dumb as possible. You need the source port so that you can send stuff back, the destination port so the OS knows where to send stuff, how much data you're sending, and our last minute checksum that we put in everything. So really simple, and that's all we really have to say. You dump stuff at whatever rate you want to dump it off at. Sometimes that is OS limited. It's smart if it's OS limited as opposed to just flooding every network that exists out there with UDP packets. There are a few pretty popular UDP protocols out there, DNS being one of them. Although maybe some of that's changing, I hear. That might be rumor. But that's UDP in a nutshell. So what do we want that goes beyond that? Since neither IP is giving us a guaranteed delivery, and now UDP is not giving us a guaranteed delivery, what we would like is some sort of protocol that gives us some connection that guarantees delivery of our information, guarantees it in order. If you can put more guarantees on it, that's great. But the first thing we need is kind of a connection-oriented and reliable transport layer protocol. Right now we have UDP, which is unreliable because it's built on this kind of best effort delivery of the internet. So to do that, we use a different protocol, and that's the transfer control protocol. And this protocol is pretty amazing. It kind of does all the things. And so there's a lot to talk about. It's going to take us a couple of weeks and a couple of videos to push through it all. But TCP is going to be the thing that gives us this connection-oriented, reliable delivery. It's got flow control in it, and it's got congestion control in it. Congestion control is so big that it has its own chapter in this book. At the base level, TCP is really just based on this connection-oriented protocol. So the idea is your application has some stuff it wants to send to some other application across the internet. You dump them into your buffer, it sends them across the internet, and then the other application receives them. So I send a, hey, give me that index page from google.com. And I make my connection to google.com. I send that data over, and then maybe the other application reads those bytes, decides to do something, and sends something back in a fully duplex sort of way. TCP is built on this sliding window protocol that we talked about way back in the physical layer days, chapter 2.5. The idea is that I can dump a bunch of things, packets, out on the internet, and the receiver can kind of acknowledge them. TCP will allow you to acknowledge a bunch all at once rather than kind of acknowledging each packet like this. And there are a bunch of extensions and things that we won't get into, but the basic idea is still a sliding window protocol that we talked about in the link layer. There are some really important differences. Some of those you're going to see show up in the header for TCP to highlight some of those differences. First things first, though, it has a sequence number. We talked about why we needed a sequence number when we were talking about the sliding window protocol, so that we knew which packet was being acknowledged kind of here on the other side. This sequence number is going to be the byte. It is a byte level sequence number, the byte that I'm acknowledging, or the byte that I'm sending, I guess. And the acknowledgement is the byte that I'm actually acknowledging that I'm ready to receive. So every packet in TCP is going to both send the sequence number of the data that you're sending, but also acknowledge kind of like what you're ready to receive in every single packet. So that's pretty cool that the ACK and the seek are kind of all set in the same packet in there. You can imagine it has to have a source port and a destination port. These are still 16 bits. The port number of ports don't change here. A normal checksum header. Flags are going to be here for the state diagram that TCP needs in order to kind of establish its connections. And this advertise window is part of the flow control, and we'll talk about that a little bit. So what are some of the main ways that this sliding window protocol is different than the link layer protocol, though? For one, the link layer won't reorganize your packets, right? So when I'm sending a message directly over a link, you can kind of think of it like, I pass you ball number A and then I pass you ball number B, and I'm kind of passing them directly to you so they don't show up out of order. However, when we dump things out on this internet, you know that they can take different routes. They can do different things. Some of them might be lost. So these things can either not show up or show up out of order. And so we have to kind of deal with all of that issue. Another issue is that a physical link will have a relatively constant round trip time. I send something, I get it back. I send something, I get it back. And a TCP connection, if I'm connecting to my buddy over here, my connection might have a 1 millisecond ping. But if I'm connecting to somebody over in Japan, I might have a 100 millisecond ping. And so I need to be able to deal with that, right? My round trip times might change. They might even change in a single connection. Maybe sometimes me and Japan are 100 milliseconds, and maybe sometimes we're 500 milliseconds. And I need to be able to make that all be part of my reliable connection. There has to be buffer space. So part of the flow control is that I don't want to send stuff faster than my receiver can actually accept it, even if my network can handle it. So flow control needs to be part of this process, because we don't want to just send stuff over the network that gets dumped that I have to resend later. That doesn't help us at all. And since TCP could theoretically flood a network, we also want to put in some congestion control. Again, we're going to talk about that later, but congestion control is a big piece of the health of the internet that TCP helps guarantee. With UDP, you really can just kind of flood networks, and that is sometimes used as an attack in different ways. Usually your OS will fight you a little bit on that, but TCP doesn't have any restrictions on, UDP doesn't have any of those restrictions natively, like the network, the transport layer itself doesn't set any restrictions. But TCP has specific rules governing how it's allowed to send traffic to help fight congestion, and to help, say if two people are using the same pipe, to help you both use the pipe fairly and evenly. So that's all part of it. And that's how it's different than just the link layer sliding window protocol. And the link layer sliding window protocol, you're connected directly, and so you have some guarantees that you lose when you're kind of dumping things out over the internet. Yeah. So what does this look like, the sliding window protocol in general? So basically what you're keeping track of as a sender, and remember, kind of both sides of this connection are both senders and receivers. This is kind of a fully duplexed sort of situation. What you're keeping track of is, as a sender, you're keeping track of the last byte that's been acknowledged by the receiver, but also the last byte that you kind of sent. But you might also have a buffer of things that you still want to send, right? So you can imagine in a voice call, right? I might have some things that I've said, and I'm waiting for you to acknowledge that I've said them, and I might have some other things that I want to say, but I'm not going to say them until I know you're ready for them. Like maybe you're transcribing what I'm saying or something like that. On the receiver's end, you are receiving messages, so you have kind of the next byte that you expect, but you also have kind of a last byte that you received. Now, it's interesting that these might not be the same, and that might be because packets got lost. The receiving application might not be caught up. So you got to remember, there is one more layer here, the application layer. So the idea here is that there's a bunch of data sitting here that the application hasn't looked at yet, but is still buffered. Your OS is dumping them into the socket, but your application hasn't kind of grabbed them out of that socket and handled them yet. So this is kind of a view of what it's like to be using the TCP protocol as an application, and a little bit of a view of how some of these numbers are being used in the header as we think about the senders and receivers here. When you establish a connection as part of a TCP connection, there's a three-way handshake. The third part of this handshake can actually have data on it. So it's still a three-way handshake because there's 3 steps that need to happen. The first thing that you do, these flags here, one of the flags is a syn flag for synchronize. And what I'm going to do is I'm going to pick a relatively kind of random sequence number X, and I'm going to tell the server, hey, I want to make a connection to you, and here's my sequence number X. And part of that is so that the server knows that you picked some byte to start sending your data as. And then the server will say, okay, I acknowledge your sequence number +1, because that's the next byte I'm looking for. And I'm going to tell you what my kind of random sequence number is. Now, we're not going to start with sequence number zeros, because if connections die and then get reestablished, we don't want them to think maybe they're still using an old stale connection. And that's a little involved, but we could talk about that online, or send me some comments if you have any questions. And then the last part is that the client, once it understands that it's been acknowledged, it knows what next byte it's supposed to send, and it knows kind of to acknowledge the next byte that it expects from the server, which is y+1, then it will acknowledge those, and it can send data along with this. So if I'm making connection to a web server, I make the connection, it says, hey, this is what the connection parameters look like, and then I can say, okay, great, I know what those look like, here's my GET request, and then the server can kind of respond with a, okay, fine, here's your web page, right? So these acknowledgements and sequence numbers, you can see, are sometimes used at the same time, and pretty much every packet after this point will use both of them, and both of them will be meaningful. So that's a good thing to remember. All right, let's switch back to our big view here. That was UDP. So let's look at this. This is kind of daunting to look at first. This is the state diagram for connections, right? So generally, everybody starts up here closed. If you're a server, one of the first things that you're going to do is listen, and there's going to be a server video that comes out that walks through that C code for how a server is set up. But you'll notice a listen call in there. And then if you're kind of a client that's trying to actively connect to a server, then one of the first things that you'll do is send that synchronization request, right? And when you do that, the server will receive it and acknowledge it, and this flow here, as you can see, like send this synchronization, receive a synchronization, acknowledge a synchronization, or send and acknowledge at the same time here is kind of important for how connections move from closed, either as a server or as a client, and what that looks like. And then there's a bunch of information related to closing down connections. Generally, we close down connections after 2 segment lifetimes. I'm not going to spend a lot of time kind of digging at why some of these things exist, but think about the fact that that sequence number might exist in a packet that bounces around the internet for a while, even after you've closed this connection. And that's part of the reason why we don't use a sequence number of 0 every time, is so that if I did reestablish the same connection, I went to google.com, killed the connection, and then I went to google.com again on my web browser, I don't want the old data coming back and kind of clobbering or intermixing with the data that I'm trying to get in my new connection. Some of that is also circumvented by picking different ports for each of those new connections, but that's the way it is. There is a method here of attacking a server called a Syn Ack Attack, and the idea is that you send to the server a bunch of just like synchronizations and acknowledgments that don't make sense, or to force the server to kind of set up a bunch of connections. And that is one way that people try to do a denial of service to different servers, is through an attack like that. And I didn't see that in the book. That doesn't mean it's not there somewhere. Just wasn't in the parts that I was looking through. Geez, there's so much to talk about here. So let's blow this up actually. 1, 2, boop. One key takeaway about how the server and the client work. is it uses this kind of rule that is kind of neat for protocols, which is a smart sender, dumb receiver. This allows the receiver to kind of be responsible for doing all of the work. The sender to do all the work of like, when am I supposed to do this? When am I supposed to do that? And the receiver to kind of just like, okay, I got what I got, and I either acknowledge or I don't. And the sender has to kind of like fill in the holes and do all of the work. And I think that's important. We talked a little bit about wraparound. If this is kind of interesting. So if you're on a 10 gigabit per second connection, the 32-bit sequence numbers wrap around in 3 seconds. And that's not a very long time for a connection to exist before sequence numbers hit each other again, which means a sequence number of 32 bits is kind of outdated now. And so there are extensions to TCP to effectively bump this up and make this better, because otherwise TCP doesn't hold up very well at higher bit rates. It was fine, back in the day when I was a young lass, right? We weren't seeing gigabits per second. And this 2-minute timeout was certainly fine for most things that we were using and seeing as end users, and it seemed okay. But backbones of internets and fiber to your house and things like that are now starting to make these times look really small. And so we have to protect against sequence numbers wrapping around. Along with that, you have to think about this advertised window as part of flow control. And the idea is that you're going to try to dictate how much stuff that each side can dump into the network before it can't really buffer it or deal with it anymore. And again, once we start looking at some of these delay times bandwidth products, you'll see that this required window size doesn't really quite do it. And so there's some extensions to TCP that provide mechanisms for effectively increasing the size of advertised windows, which is what it says here. So that's kind of important. Now, some of these details are probably a little hairy to you, right? We're just kind of touching on the very surface. There is very cool stuff tucked in here. Congestion control is still something we haven't talked about. How do we figure out how fast we can send data according to the internet? How do we figure out what our round trip time is? That is something that is tucked into this section in this chapter. All of that is active research. There's a couple different ways that you can do it. There's a couple different mistakes that you can make too, which are really interesting to look at. But our video is getting kind of long, so I'm going to stop it here. As always, take care of each other and take care of yourself. Bye.